So today we'll continue chapter 8. This is the picture of explaining the idea of what we are trying to say in this chapter. So in this chapter we are trying to explain the criterion for phase equilibrium. Okay, so phase equilibrium, this is the phase transition, the case at which you will see different phases exist at the same time. Okay, and we started with entropy, and we said entropy can be used as one of the criterion for phase equilibrium, but in order to use entropy we need to calculate total entropy, which is summation of entropy of system, entropy of surrounding. Not all the time you can calculate entropy of the surrounding, so we need to replace it, and we replaced it with Gibbs free energy. And we said that, or we relate Gibbs free energy to entropy, and we have an equation, and this equation contains a negative sign. So this means for any process to occur spontaneously, the entropy is increasing, but for any process to occur spontaneously, Gibbs free energy will decrease. So this is why we have minimum Gibbs free energy as the most stable case. At phase equilibrium, like if you have two phases, liquid and vapor phases, for example, how I know that these conditions represent equilibrium conditions? By calculating molar Gibbs free energy. If molar Gibbs free energy of the liquid phase, molar Gibbs free energy of the vapor phase are equal, so this means at these conditions you have phase equilibrium. At these conditions you will have liquid and vapor phase exist at the same time. So this is the key here. We have equality of molar Gibbs free energy for the different phases. And again, the equality for molar Gibbs free energy, intensive Gibbs free energy, not extensive Gibbs free energy. And we relate molar Gibbs free energy to something called the chemical potential. And we said in this course we are focusing on pure substances. For pure substances, we have them are equal. Molar Gibbs free energy, chemical potential are the same. When you start studying thermodynamics too, you will see that molar Gibbs free energy, chemical potential are not the same for mixtures. But for pure substances, they are the same. Okay. And last thing we said, for Gibbs free energy we have one limitation, that we cannot use it for mixtures, as we said, and at low pressure values the value of molar Gibbs free energy or chemical potential can be negative infinity. This makes solving the equation or making trial and error sometimes difficult in this one, and this is why we will talk about a new property, fugacity, which is, as a definition, this is a corrected pressure. Okay, so we are using this thermodynamic property, this fugacity, in order to predict phase equilibrium conditions. And the rule is the same. At phase equilibrium condition, fugacity of liquid equal fugacity of vapor. Okay, so if you are trying to calculate fugacity of each phase, if you have this curve present fugacity of liquid, this dotted line present fugacity of vapor, so this intersection will give you the pressure and temperature, or in general the conditions at which phase equilibrium will exist. All these two phases will exist together at the same time. Clear? Okay, so now we need to start talking about what is fugacity, how we can calculate fugacity. And again, the same approach of the problem will be similar to what we did in previous lecture, that we need to calculate fugacity for different phases and then find the conditions at which fugacity for different phases will be equal, and this will be the conditions of phase equilibrium. So what is meant by fugacity? Again, if you remember from chapter 2, we said as pressure decrease, so any real substance, especially gases, will behave as an ideal gas. So this is why we can say, and this is one of the limitations of Gibbs free energy, the limit of value of molar Gibbs free energy when pressure tends to zero can be negative infinity. Okay, so this means if you have limits when pressure tends to zero of molar Gibbs free energy for real substance minus molar Gibbs free energy for ideal gas, so ideal gas automatically the pressure is low. For real gas, when pressure equal to zero, so this substance will behave as an ideal gas. So the value of molar Gibbs free energy for real substance minus molar Gibbs free energy for ideal gas at very low pressure, this is equivalent to zero. And do you remember what we call from previous chapter the property for real substance minus the property for the same substance at ideal conditions? Anyone remember the last thing we discussed in chapter 6? Residual property. So we have this one here, G minus G at ideal gas. This is residual molar Gibbs free energy. Okay, so this is the like the fundamental rule we have. So we can say limit of molar Gibbs free energy when pressure is low, this is almost zero. Okay. So this is the rule that we will start using in order to build the mathematical representation or find the mathematical equation of fugacity. Okay. So again, from chapter 6 for isothermal process, we have the change of molar Gibbs free energy for ideal gas can be calculated from this equation, which is RT d ln P. Okay, so this is the equation that we can use to calculate molar Gibbs free energy for ideal gas. Usually the equations we are using for ideal gases are simple equations. We prefer to have this assumption because ideal gas equations are simpler than real gas or real substance equations. So this is why here, since this concept is residual molar Gibbs free energy, and residual molar Gibbs free energy is molar Gibbs free energy for real substance minus molar Gibbs free energy for ideal gas. This is the equation of molar Gibbs free energy for ideal gas. So we need to have a simple equation similar to the equation that we are using for ideal gases, but this equation will be applied to real substances. So if we need to calculate the molar Gibbs free energy for real gas, I need to use this simple equation. So I will use this equation. R, this is the ideal gas constant. T, this is temperature. But instead of using pressure, I will use a new term. I will call it F, and this will be the fugacity. And this fugacity includes, this fugacity is considered as a correction of the pressure. So the whole idea that's where fugacity comes from, that we have ideal gas equations. These ideal gas equations are very simple. Direct, we can directly use this equation, substitute in this equation, find the property we have. For real gases or for real substances, the equations are much more complex and we need to avoid this. So we will use the same equation that we are using for ideal gases or ideal substances, okay? But we need to correct these equations. And the simple way of these equations that we need, instead of using pressure, we will use a new property. It's called the fugacity. This is why in the previous slide, when we explained fugacity, we said it's a corrected pressure. Okay, we are using it instead of pressure that is used for the ideal substance equation for molar Gibbs free energy, but this is only to correct the property we have. And if we start to apply this concept, which is limits of molar Gibbs free energy equal to zero, by using this equation and this equation here, then we can say that the change we have in residual Gibbs free energy, which is change of molar Gibbs free energy for real substance minus molar Gibbs free energy for ideal substance. So put the first equation for real substance, second equation for the other substance, then we can say the change of residual Gibbs free energy is nothing but this equation. Okay. And we can rewrite this equation in order to end up with this form here. And this will be the equation that relates fugacity to residual molar Gibbs free energy. And this is how the definition of fugacity or mathematical representation of fugacity start to come from. So again, when we start with finding criterion for state equilibrium, we start with entropy. We have limitation with entropy. We used Gibbs free energy. But we relate Gibbs free energy to entropy. We have some limitations on using Gibbs free energy, so we introduced a new property, fugacity. But at the same time, fugacity is also related to Gibbs free energy. So everything, all of these criterion are related together. Fugacity related to Gibbs free energy related to entropy, so everything is completely connected. This is why we have the same concept in all of them. At phase conditions, the value of this criterion for all phases will be the same. Clear? Any questions so far? Okay. So again, this is the equation we have that relates this corrected pressure, fugacity, to residual molar Gibbs free energy. To simplify the equation, we will replace fugacity divided by pressure with one simple term. We will call it phi. Okay, so we can rewrite the equation and say ln phi is residual molar Gibbs free energy divided by RT, and this phi is called fugacity coefficient. So fugacity coefficients, they are the same. Both of them can be used as criterion for phase equilibrium. Okay? And the same thing, since we talked, or we said in previous lecture, for phase conditions, for change conditions, or phase transition or phase equilibrium, molar Gibbs free energy for the first phase equal molar Gibbs free energy for the second phase. Gibbs free energy related to fugacity. So fugacity for the first phase equal fugacity for second phase at this phase equilibrium conditions. Or fugacity coefficient for phase 1 equal fugacity coefficient for phase 2. Okay? And the advantage of using fugacity instead of molar Gibbs free energy, that by using fugacity or by using fugacity coefficients, we will not approach this negative infinity extreme at low pressure. So this overcomes the limitation that we may face with using molar Gibbs free energy. Is it clear? But it had the same thing, exactly the same thing. Okay, the lowest possible value for fugacity will be 0 because the residual molar Gibbs free energy can be 0 at very low pressure. So we are just avoiding this negative infinity values that we can find with molar Gibbs free energy. Any questions so far? Okay. So just to give you a summary, so fugacity, this is a corrected pressure. We are just using or defining this fugacity to be able to use simple mathematical form for ideal gases, but just we need to use this equation for real substance. So we are using fugacity instead of pressure. Fugacity and pressure, they have the same units. Okay, exactly the same units. Okay, fugacity is like this is describe the escaping tendency of your substance. So how your substance have energy or driving force to escape from one phase to go to the another one. So this is why it's used as a criterion for describing phase equilibrium. And quickly we have, as we said, phase equilibrium will exist if we have equal fugacities for the two phases exist at these conditions. At very low pressure, real gas behave ideally, so fugacity and pressure will be the same. At low pressure, there is no difference between fugacity and pressure, but at high pressure or near condensation, where the interaction or intermolecular forces between molecules become significant, then fugacity will not be equal to pressure.